I don't know all the rules of the college, but I think it's okay because I know other colleagues do that. So I will confirm this week. This course, the deadline is on the 5th, but if possible, we can move it a little forward if you like. But it's not necessary, right? You will not hate me if I don't move it. I like to please the student. However, you're already seeing the course, so I cannot move it too much forward, right? Otherwise it's a little bit unfair. Right? But so the 5th is on a Friday, so we can move it. Okay, so we can move it on okay, we can move to Friday for sure, or perhaps on Monday if you want to work with the weekend, but it's not. Maybe the weekend is nice to take a break. So you see, when you have an extension, you pay some price. The price that you get to work during the weekend, whereas if you work hard until Friday, so I will move it to Friday. But if you want to Monday is okay. I will not go longer because you have already seen the assignment. So I think this is kind of okay. So we can decide next. But work on the 5th of December deadline because I need to get it confirmed with JJ. But I assume it's okay, but not 100% sure.
Do we have it in
to JJ.
You talked about your assignment as well.
So I was saying that the deadline is on the 5th of December. If it is okay with JJ in the office, collect the assignments, we go to the 7th. No, this is a holiday.
Also, 1, 2, and 3 need to be handed in some code.
Yes, but for this one is some math. And I prefer to have it physically with JJ. It makes my life easier. But that's how we do it. That's the same for supervised learning. I'll repeat next week. So, any questions? Yeah. Did you know already what we saw in the first hour? It was useful. It looks very easy. Right? You have no questions or completely useless. I don't know. So, we are not done, just 5 more minutes to clarify the last point. But the last point is that PCA can also be seen as a low rank matrix approximation, right, of the data matrix. So what we've seen so far is that the principal component analysis can be interpreted as the linear transformation of the data which maximizes the variance, or equivalently as the linear transformation of the data which minimizes the average reconstruction error. Right? They are completely equivalent. And we can also, in this last part, go back to the singular value composition, and we see that principal components provide best low rank approximation of the data. So here we remind the single value composition, right? So the notation that we use at the row of the matrix X are the data points, right? So by X I mean the matrix which has as the first row X1 transpose and then X n. Right? So n is the number of data points, and D is the dimension of points. So I can write this as U sigma V transpose, right? And U and V are the eigenvectors, the singular vectors, right? So U and V are orthogonal matrices. And sigma is a rectangular matrix which on the diagonal has the singular values. Singular position. Now what we can see is following. Okay. So we go back to our second interpretation of stuff, right? So the problem would be to minimize this, right, over Q and over all these vectors Wi, these coefficient vectors, right? But this is just some algebra basically. So once you get the algebra right, you see that this formula is nothing new. So I just rewrite this as the Frobenius number square of some matrix, right? And the matrix is Q transpose minus QW, right? Well, W is the matrix which has as columns the coefficient vectors for each of the points, right? So here I put X transpose because now the matrix X transpose has as columns the data points, right? And if you think about it, what this says is this is the sum of the square norm of the columns of this matrix, right? And the ith column is exactly xi, the ith column of X transpose, right? Minus the ith column of Q times W matrix, which is Q times Wi. Okay, so complicated way to say the same thing, right? So X transpose, because of our notation, is now a matrix which has the points as columns, right? So if you select the ith column of this is xi, and the ith column of this matrix is the first matrix times the ith column of the second. That's how you multiply matrix times. So I can rewrite my objective function as now a distance between these two matrices. And now what I need to realize is that this matrix Q times W, right? So Q is a matrix which has so normal columns. W is a matrix of coefficients, right? This matrix, Q times W, has rank at most k, right? Because it's a factorization of a big matrix, right? So Q times W is, what is it? D times N, right? Let's imagine that D and N are both large, right? But K is small. So K would be less or equal than the minimum between D and N, and possibly much smaller, right? So there is a bottleneck. So that the rank of this matrix is controlled by K, right? By the number of columns of Q, right? The numbers of rows of W. So the problem is the same as this guy. So we minimize the distance between X and a rank K matrix, right? So here, to confuse you, I have just done one more step, which is not there. So I can rewrite this also as X minus W transpose Q transpose. I think this I call Z, right? All these transpose annoying thing is because we write the matrix X this way. That's the notation we use in many parts of the course. So to summarize, right, so the problem of looking for the best k-dimensional linear representation of data is equivalent to right, so which is the representation which maximizes the variance is equivalent to solve this problem, so to minimize the average reconstruction error. That involves the matrix Q, right, which is the matrix of our vectors, and the matrix of coefficient W, which here we pretend it stays by itself, but we know that we minimize over W fixed Q. There's a simple formula. We ignore that. We write it this way, and then we change the problem by saying that, or what we say, that this matrix should be ranked at most K. Then we see that the problem is equivalent to a low rank approximation. And then we don't prove that, but we can show that the solution of this problem, right, actually it follows from what we have seen before. the solution of this problem is given by taking the leading singular value decomposition x. Right? So that's another way to see this stuff. So more precisely, you see that z will be equal to x times b k bk transpose. Right? So that we find this matrix. Right. Yes.
The norm of x minus z, that the Frobenius norm, is that correct?
Yes, absolutely. Absolutely. Yes. Yes. If we change that norm, something else could happen. So this is interesting because, yeah. There are some, but this is just as a digression to conclude this lecture. There are some interesting problems which start from this formulation. Right? So, principal component analysis is normally introduced and described the way we've done it before. So as a way to maximize the variance or minimize the reconstruction error. But these low rank matrix approximation are also interesting and used in the area, for example, in the problem of collaborative filtering. Maybe you have heard of that. Right? So when you try to approximate a matrix x by a simple matrix, low rank matrix. So this problem can be solved by the SPD, is equivalent to PCA, but you can imagine an extension of this problem where we change this norm. Right? In particular, one which is considered, for practical reason, is one which considers only some elements of the matrices. Right? So this is what they do in collaborative filtering. So they have a matrix X that they only know the partial information about it. So there is this, for example, this Netflix data set. We used to have a competition a few years ago. And actually there was a guy here in Kentish Town, working in a garage. They had one of the best systems at some time. At some point, and he came here to give a talk about how we got this performance. So what was the problem? The problem was, knowing only some elements of X, find the other, the remaining, right? And there was a clear rationale for doing that, which is that the rows of the matrix were referring to movies and the columns to users, right? And every time you know an entry, you know that that user likes that movie, or perhaps between 0 and 5, 5 means likes very much and 0 dislike. Right? And you only knew some entries of this matrix X, maybe a few small percentage. However, how can you find the remaining entries? You only know 1% of the entries of the matrix. How can you find the remaining entries? So if you find them correctly, you make a lot of money because you can predict what people will like. So you show them these movies, right? You show the movies which have the largest value in the predicted matrix, and it is more likely that they will rent it, they will buy it, it works, and so you have made a very efficient recommendation system. And so the point is that if the underlying matrix, which describes people's mind, is low rank, and this is a big question, is it true? But if it is true, then you can still find it from limited information. Namely, you only know a few entries of the matrix X, but you can extend knowledge of the full matrix by low rank approximation. Right? And that works to some extent. It works. And however, the problem is not easy anymore. So this problem is easy because it can be reduced fully to single value decomposition. And as you know, you go to MATLAB, press a button, and you have the solution in polynomial time. Whereas this problem, if you change this norm to be partial information, is NP-hard. Right? So there is a big question: how do we solve it? And so this is for another time. So this is something that you see that these classical tools, which are known for several decades, also play an important role in say, more recent research. So, any questions? Can I go a bit too slow than the lecture? Or faster? I must say that before the break you were more alive. So I don't know how to interpret these cycles. So it's so I will not. I will stay. I will continue with that. So the purpose of the main part of the course is to show you something which is a bit complementary but related, because it still has to do with data representation, right? So PCA is data representation, dimensionality reduction, and here we see an approach which is more recent. The principal component analysis was probably developed, I confess by ignorance, but I think is before the 30s. Double check. Because canonical correlation analysis was developed in the 30s and is a more general technique, so this probably goes back to 20s, 10s. And it might be the case that it was developed here at UCF. Here there was all this. They still had the part. And there was a Carl Pearson. My apologies. So which was one of the most famous statisticians. And what we see now instead is a different method, which is more recent, and perhaps it comes more from computer science. So, and it is based on the idea of building graphs and doing some operations on graphs. So we will change quite a bit the topic. However, as you will see, since this is not a course on machine learning per se, as you will see, the tools which are used are there's common ground. So perhaps we have seen from Markups a little bit about spectral clustering. Do you? Or Markups has spoken with the supervised learning about spectral clustering, or what about unsupervised learning? No. Okay, so then this lecture is about something which is new, I guess, that we have not seen earlier. So, right. So the goal is the same, the tools, the approach changes. For this reason, I first recall some notions of graph theory, very elementary. There is much, one could say much more, but introduce just the minimum required to describe what Laplacian eigenmaps and spectral clustering are. Also called graph embedding. So first describe what the graph Laplacian is, then the graph embedding, also called Laplacian eigenmap, is a way to represent, so it has the same aim as principal component analysis, to represent the data points by smaller, lower dimensional vector. However, the way it is done is completely different from PCA. In particular, is a non-linear representation of the data. So PCA X is represented as Q transpose X. It's a linear transformation, very special linear transformation. Here, these graph embeddings are a non-linear transformation of the data, which use the notion of graph Laplacian to achieve the transformation. And then I'll discuss clustering, spectral clustering, using these ideas. So but it is just see. So this is an undirected graph. So you have finite set V, which is a set of vertices. You can just think of it as the number 1 through n, right? And then you have a set of edges, right? So the set of edges is a subset of the cross product of V by set. So the same thing as V is just equal to 1 to n, right? Or perhaps V1 through Vn, so the vertices of the right? So, and the edge set is a subset of this, symmetric, right? And associated, the graph is the adjacency matrix, which has the property that Aij is equal to 1 whenever the vertex, the edge I comma j is in the graph, appears in the graph. Right? Okay, so you have something like that. You have 4 vertices, and you have this graph, let's say, right? 1, 2, 3, 4. So in this case, the adjacency matrix is 4 times 4, right? And then you have that the diagonal is always equal to 0 by definition. And then you have that 1 is connected to 2, so you put a 1 here. 1 is not connected to 3, you put a 0. It's not connected to 4. 2 is connected to both 3 and 4. 1, 1, and 4 is connected to 3. Right? Then it's symmetric. You put here the same as that. So this is the it's called the adjacency matrix. Another important thing is the degree of the vertices. So this vertex has degree 1 because there is only one edge associated with vertex. Vertex 2 has degree 3 because there are 3 edges. And the diagonal matrix D is the matrix which has along the diagonal the degree of the graph, of the edge of the vertices. Yeah.
Vertices not be vertices not be connected to themselves.
Yeah, we exclude that possibility. Yes, yeah, we exclude self loops are excluded. That's right. Otherwise, it goes in diagonal. So, and yeah, way to write. So Dij is, we also use this notation, is equal to Di, the degree, times delta Ij, because it's diagonal. And Di is the sum from n, from 1 to n, of Ai n. So it's a sum of, counts the number of edges which are associated with vertex I. So here is important, the graph is undirected, so it doesn't matter if I put Aij or Ail or Aili, the same. Okay. So I will repeat this if you need to see it again. Okay, so now we want to understand what the graph Laplacian is. Consider this quadratic form. So this is one vague similarity we see. There is a quadratic form involved also. So we take a vector x, right? Not to be confused with the data point. This is just the vector x, right? And xi are the component of this vector. Okay. So x is an n-dimensional vector. And we consider this function, right? It's a function of x. And this is a quadratic function, right? And it's a sum over I and j, so 1f, aij, and then the square difference between xi and xj. Okay. This is a quadratic function of x, right? And it is also a positive function, right? Because aij, adjacency matrix is more or equal than 0 element-wise, so the function f of x is more or equal than 0. Right? So this can be written as a quadratic function, quadratic form, for some matrix M. That is the Laplacian. That matrix M, which allows you to rewrite this in this form, is the Laplacian, and now we see how it is constructed. Right? And the way to do it is just to do some expansion and recomputation of terms under the sun. So what we do, we have here the square, xi minus xj squared, we expand it. Right? So we get here, we get xi squared plus xj squared minus the cross product. And then we use the fact that A is symmetric. Right? Since A is symmetric, this term, right, when they are sum over I and j, give the same result. Right? And when you sum, for example, over j, the first term, since j appears only the matrix A, right, you get the degree, you get the I, right? So the result is indeed this weighted square norm. The result is the sum over I, xi squared times di. That's the result of summing up the first two terms. Is it clear? So what I'm saying is that this stuff by symmetry is just equal to this. So I can remove the 1/2 here and just do that, because it's completely symmetric. Right? If I change I with j, I obtain the same thing. Let me be more explicit. This thing is equal to this. Right? But I have the only difference that I here becomes j, but it's the same because A is symmetric. So I can recall my index I with j and vice versa, so it's the same. And then, if you look at this, you first sum over j, and you get the sum over j, dij is equal to di, right? So you put it here, you sum over I, and you get this. The second term is a quadratic form which involves the matrix A with minus sign. So that the whole thing can be rewritten as this sum where this matrix appears, dij minus aij. Right? Where dij, where d is the degree matrix, so it is equal to di delta I, what I wrote in the previous slide. So this is the Laplacian. Right? The Laplacian is the degree matrix minus the agency matrix. And by construction, it is a positive semi-definite matrix because this quadratic form is always more or equal than 0 because it's equal to the first expression, which by definition is non-negative. Okay. So this is interesting because if you take a vector x, any vector x, right, and you consider this quadratic form, this can be interpreted as this, right? So what you do, you take every neighboring vertices, right? You take the different square of the vectors and you sum it up. So another way to rewrite this is as sum over I and j in the vertex in the edge set, right, of xi minus xj squared. And I guess you need to have, yeah, that's correct. Okay. So there is a mistake. Yes, so I think it depends what you define as the edge set. Right? So if it is cuts the edges only once, here you cut it once because you have I, J, and J now. So now we want to understand what we can do with this. We can use these formulas to gain some intuition about what is a good representation of the data. I still haven't described what the data are. Right? So at the moment we just have a graph. So for graphs, at the moment we just want to find the representation of the graph, which is a bit less unclear what this means. But in a moment I will elaborate. So okay. Before doing that, let's look at the eigenvectors of the Laplacian. Because the Laplacian is symmetric or semi-definite, so it has non-negative eigenvalues. Associated are something first. So I can go to MATLAB, as we've done in the break, and find all the eigenvectors. Okay. So I choose my matrix A. For example, it would be a random graph. Every edge is either 0 or 1. The elements of A. Right? I build the Laplacian, and I compute the eigenvalues, the eigenvectors. And what is the meaning of these eigenvectors? That's the question. So first of all, the first eigenvalue, the smallest, is equal to 0. Right? And the reason is that if you take x to be equal to constant vector, the quadratic form is equal to 0. Right? Because if you take differences, so if all the components of x are equal to the same number, the quadratic form is 0. So therefore, lambda 1 is equal to 0, and u1 is equal to a constant vector that here I have normalized so that it has normal 1. So all the components are equal to 1 over root n. Okay, so this 1, here you don't see what is in bold, so it's an n-dimensional vector. Okay. Sometimes you also write as E1n, so it's meant to be an n-dimensional vector. What about the other eigenvectors? Well, first of all, are there any other, what about the second eigenvalue, lambda 2? Is it equal to 0 also, or is it equal to a number more than 0? Well, what you can see is that if the graph is connected, then the second eigenvalue is different from 0. So it's strictly greater than 0. That's a good thing. The number of connected components of the graph, what is the number of connected components of the graph? Is the cardinality of the smallest partition of the graph into connected subgraphs. So a connected graph is a graph where every two nodes you can go from one to the other path, right? It's define what the path is, but I think this is intuitive what it is. So you can move from one vertex to another one, keep walking, and you reach the other node. So every two nodes on the graph are connected. If that is not possible, so if there is a node here, and a node here, which are not, there is not a path, the graph is not connected, and then you can ask yourself, what is how many connected components the graph has, right? And to find the number of connected components of the graph, what you can do is to look at the eigenvalue decomposition of the Laplacian, and then you see the degeneracy of the zero eigenvalue, and that counts the number of connected components of the graph. So if it is 1, it means the graph is connected. If it is 2, there are 2 connected components, and so on. Right? In particular, if lambda 2 is more than 0, the graph is connected. It's not difficult to see this. I'm not describing in detail. But one way it is very intuitive. So because if you have, let's let's say, a graph which consists of two connected components. This graph, right, what we saw before, and then we have, say, this. But this is not connected. There are two connected components. Then it's clear that if you choose this x equal to, say, c, if I belongs to the first component, let's call it p1, and 0 otherwise, then this has 0 eigenvalue, right? Because the quadratic form will be equal to 0. Right? The sum of I and j, 1 to I, and j, I plus j squared, is equal to 0. Right? And likewise, if you choose x to be, so let's say, this v1, v1i is equal to v2i is equal to 0 if I is v1 and is equal to some constant, we need to determine I is not in v1, so it's a complementary set. This has also quadratic form equal to 0. Right? And these two vectors are orthogonal to each other. So you see that there are at least two eigenvectors with 0 eigenvalue, but they are exactly 2. We cannot do more than that. So computing the number of connected components of the graph is easy because we just do an eigenvalue decomposition and Laplacian to count the degeneracy of the 0 eigenvalue. It's an easy combinatorial problem. So, having said that, we will assume that our graph is connected because we don't lose generality. We assume we have a graph which is connected, and so now we go back. Before going back, I do an open a parenthesis because it's important. Why we are talking of graphs, right? So because I was talking of data representation and PCA, so why we talk of graphs? It's a bit abstract so far, right? But the point is that if you have data and you want to find a data representation, you first build the graph, and then you think of embedding the graph into a low-dimensional subspace. And so that's the way to achieve a low-dimensional representation, to do dimensionality reduction. So you get points, but here I call them T1 through Tn because x was used before to denote a generic vector. So I have a point in b-dimension. I've changed bit notation from the previous lecture. And what I can do, the points are in the space. Let's just imagine they are in the plane. I can build a graph using some proximity matrix, right? So for example, the Euclidean matrix. So I can compute the k nearest neighbor. Now this k doesn't have to do anything with the dimensionality. It's just a k of the nearest neighbor. So for each point, ti, I compute the k nearest neighbor of ti, or the k nearest point. And then I decide that the point I is connected to the point j if either j is one of the k nearest neighbor of I or vice versa. Right? So this way, right, so I have to say these points, and let's try to do an experiment. Complicated. Let's take k equal to 2, right? So this point is a k nearest neighbor of this, so they are connected. And the next one is maybe, I guess, this one. They are connected. This one as first nearest neighbor is this one. We are connected. This is the second one, right? And this one as its first nearest neighbor is this one, and I guess this one, and so on. So you extend that, right? So this way you build a graph which has as vertices the points, and the edges correspond to this figure one building its neighbor of the other, or vice versa. Right? And so this graph represents, in a way, the proximity between the points. And So now we will see that by looking at the graph Laplacian, these eigenvectors of the graph Laplacian give us a representation of the data, low-dimensional representation of the data. Here, we will choose the eigenvector which corresponds to the smallest eigenvalues, not the largest. So that's the way from data you build a graph, and by looking at the graph Laplacian, you do a linear representation of the data. You could also build a weighted graph, where, for example, you decide that Aij, so here Aij is equal to either 0 or 1, standard graph, but it could also be, for example, this weighted graph. Everything is connected, but then you have a parameter beta, and then you put Ti minus Dj. Okay. This is like, there's always an edge between every pair of vertices, but if they are far away, there's a small weight associated with the edge. The Laplacian is also defined in this general case. We skip this part. But the same considerations apply pretty much. Let's consider the case in which then we have a standard, unweighted, undirected, unweighted graph. So we want to study an embedding of the graph. Right? So this embedding is a way so we replace every vertex of the graph with a vector, say one-dimensional vector. We replace each vertex of the graph with either one number, two numbers, or so on, depending on which dimension we want to, depending on the dimension of our representation. Okay, so if we replace each vertex of the graph with one number, we do what is called linear embedding. So we find a transformation of the graph to a line, right? So we have our graph, say, is 1, and we want to transform the vertices, want to map it to the line. So say this point will map here, and this point will map here, and this one will go here. Just imagine it like that, and this will go here. Okay? So that's what is a linear embedding. Yeah.
There, the xi and the xj's, they data points.
No.
N-dimensional, sorry.
Not at all. The x here is a variable which will give us the representation. So the notation is misleading. I agree with you because in the previous slide that was data point. So here x is a variable. So if you like here, so x here is the variable through which we will find a new representation of the data point. The data point is I. So I is the vertex I, which, as we saw before, so let me repeat it. We have a graph. Okay, the graph can be a result of a process done to my data set. Right? So, yes. So the graph may be built from data points, which I call T1 through Tn. So T1 through Tn are, say, images of faces. My favorite example are faces, and then you look at two people. If they look very much similar to each other, so I don't know, you are one of the Trini's neighbor of Andrew, then I put a link. Right? So I take data points and I build a graph using this nearest neighbor process.
Euclidean distance to the nearest neighbor.
The distance will be some distance.
Some
Euclidean distance. But it doesn't need to be any distance. So, in fact, that is an important part. I cannot tell you the whole story, but which distance you use will give a different graph, right? So that's also an important part, which distance I use. Let's pretend that we just use Euclidean distance. So we have built a graph. But what I'm saying could also also applies if you just start from the graph and don't be bothered by picking up data points. Okay? So I can start from a graph because maybe there are some applications in which I'm directly given a graph. The graph has a direct meaning to me, rather than being a way to, rather than being an object associated to data points. Okay.
So in the next slide, the xi's and the xg's will just sort of scalar value.
Yeah, exactly. Yeah, there are some scalar values which will determine my representation. Yes, exactly. So I have this graph which could be built from data, and I want to find a representation of the graph, right? Which simplifies my task. So instead of thinking of this graph, which I cannot even visualize because it's an abstract object, for example, if I replace each vertex by two numbers, I can represent the graph as something on the plane, right? So I can visualize it. I can see how it looks in the plane. Right? If I represent it by one number, I can visualize it on the line. So the line is a bit perhaps too simple. But I would say on the plane or on the three-dimensional space, I can visualize how the graph looks like. And then the idea, maybe here you have an exercise for markups, that is that suppose that the graph is built from the digits. Right? So these T1 through Tn are images of one of the 10 digits many times. So you have maybe 34 images of digit 1, 70 of digits 2, and so on. Right? Now, typically what will happen is that if you take one digit in the class 1, and say you build the graph from 3 nearest neighbors, so you look at the 3 nearest neighbor of digit 1. Most of the time, these 3 nearest neighbor will be from class 1 as well, right? So most of the time, what will happen is that there is a link between two points, two digits of the same class, right? And then when we will do these embeddings, right? So we have our graph whose vertices are data point digits. When we do the transformation of the graph to a line or dimensional plane or whatever, we will see that the digits in the same class tend to be close to each other. So this is where we are going. Okay? So, right. So here I want to find my representation of the data so that I minimize my quadratic form, right? So why do I want to do that? There is a clear reason for which I want to do that, right? And the reason is that if I is connected to J, it means they are similar, right? Because the matrix A is built by this notion of, so in actually the graph means that the two guys are similar. Right? In the case of the digit is clear, right? So the distance, if one of the two is the nearest neighbor of the other, I put an edge, right? Or this applies also to the case in which A is a positive number, which is like the e to the minus the distance between the two, right? So every time I and j are similar, I want to make xi close to xj. So xi is the representation of one-dimensional representation of vertex of data point I. Right?
So it just says that x is n-dimensional. It says that x is number r.
X is n-dimensional because there are n objects.
How does it, you can't subtract and square that, but if you have two x's, then how does that work? Subtract and square it.
There is one x. There is one x. At the moment there is one x.
Oh, so xi is the dimensions, so xi is the ith dimension.
Yes, absolutely, yes. So xi is the ith coordinate of vector x, right? Because x is an n-dimensional vector, right? Xi is the ith coordinate, and here I put some constraints, play some tricks. The sum is 0, right? And the vector x has no node. I put the sum to 0 constraint because I told you before that if I choose a constant vector, right, this is equal to 0, right? And this constraint can be interpreted as saying that it is orthogonal to the constant vector. So x, vector x, which I seek, should be orthogonal to the constant vector. So the sum of the component of x should be equal to 0. And this is just a normalization constraint to avoid that. All components of x should be equal to 0. The solution of this problem is equal to the second smallest eigenvector of the Laplacian, right? Because this stuff is equal to x transpose x. So here we minimize rather than maximize, so we take the second eigenvalue of Laplacian. So, and we call this U2. U1, as we saw, is 1 over root n. Constant vector, and the solution of this problem will be U2, whatever it is, the second eigenvector of the graph Laplacian. And this is my linear embedding, and perhaps let me tell you something important. Yes, I think we didn't discuss this line. Okay. So what is the interpretation of the eigenvectors in Laplacian? Okay. Well, you look at the eigenvalue equation, L of x is equal to lambda x. Right? And you can rewrite it in this form. Right? Because L is equal to d minus a times x equal to lambda x. So from this, right, if you take the ith, and this we rewrite in the other way, like this, lambda x, and I take the ith coordinate. So lambda xi is equal to the ith component of this guy, so it would be vi xi minus sum of j a ij xj. So I have rewritten the eigenvalue equation component-wise, and then you can look at this. We have this equal to that minus that. This I can bring this side, right? So I can do xi times, actually I do the opposite. So xi times di minus lambda I minus lambda is equal to this. So I can rewrite my eigenvalue equation this way. Xi times di minus lambda equal to sum over j, aij, xj. And then I divide by that, so I obtain this equation. This equation has a meaning, because if lambda is very small, right? If lambda is 0, right? This equation says something very interesting, because it says that xi is equal to the average of its neighbors, right? Because this sum goes from 1 to n, but it only involves the j which are connected to I, right? So here, what this is equal to is the sum of the values of x in the neighbors of vertex I. Okay. This is very important. So let's do that with an example. So I have this graph, right? And let's say that here I is this vertex, right? So there are three other vertices which are connected to I. Right? When I compute this sum, right, so I have, say this is x2, x1, x3, and x4. Right? When I compute my sum for I equal to 2, right? This sum will be equal to x1 plus x3 plus x4, right? What this equation will say is that x2 will be equal to the average of these three other guys. Right? So what this equation says is that every value of x is the average of the neighbors. And if lambda is small, we are not far from that. Right? So this formally, roughly speaking, can be interpreted as the smaller lambda, the more regular, the smoother, but I would prefer to use the word regular, the eigenvector is, in the sense that the value in a vertex tends to be close to the average of the values in the neighborhood. So this is a way to measure regularity of the graph. Right? So I take a vector x, and this vector is a regular vector, right, relative to the graph, if every vertex I take, the value there of x is close to the neighborhood, the neighboring average. So this is very interesting. And of course, if lambda is equal to 0, just put all x equal to a constant, that is true. But here, so going back to what we were saying before, if I do my linear embedding, the solution of this problem, which is the second eigenvector, will be so it would be something like this. So this guy is close to this, so maybe we'll go here, and then this one will go here, right? And then I don't know about these two. Here I lose intuition, but they will go here somewhere. Right? So you can try to do it. But so this embedding tries to preserve the similarity, which is associated with the graph.
Just in that previous slide, you said the eigenvector was smooth. What does it mean for a vector to be smooth?
Take it back. Regular. Regular. So it means what I said. So that if you take every component of the vector, and then you look at the components which are neighbors. Right? So the components are associated to vertices. You take a vertex, take the component of x of that vertex, you take the neighbors, and the average of the neighbors is close to the average of x over the neighbors is close to the value of x of the vertex. I think we can stop. I propose 5 minutes because the previous break was quite long, and we are still in the middle of this lecture. So don't go too far away. Yeah, then we got so this works for us. So then we will need to require. So then we will separate it. This doesn't make sense. Oh yeah, we will measure it. I think it will be useful.
How's it going, Jacqueline? How are you getting on with the course?
I'm so tired.
I was planning on working later, but I can't.
No, I got a problem. I need surgery on the
Oh, right, okay. Oh, nice.
Sometimes I write with the left hand and the right hand.
Ambidextrous.
But I'm so slow.
Oh, no, that's...
And you?
Yeah.
You are fine.
So I'm tired. No, I'm tired. I need to finish off for Friday. I need to finish the supervised learning. I need to start this next week. So I've got a lot to do.
Me, I am not finished for the homework.
No.
After I will start
Let's start that one. Who are you working with on that one?
nobody.
That's the long piece of work. I would find someone to work with.
But because I've got a problem, it's difficult to say to somebody, I work with you if I haven't finished.
Have you spoken to the college now? They know that you've got the problem. Because it might give you more time to get it done.
But at the beginning I say no more time. But now it might be a mistake.
If you if you want to discuss any questions, let me know.
Yeah.
See if I can help you.
At the beginning, I was working on the selection.
Yeah.
I was doing the assignment. Now I'm always doing the assignment.
Trying to support you.
I have no time to learn.
Oh, I see. Yeah.
But then when another assignment comes,
Yeah.
completely new.
Yes, I know what you mean.
Become harder and harder.
Try and maintain what you're doing. It's tough, isn't it? I know what you mean. I think it's the same person, so that's all I say.
And I spent so many times over the weekend.